Somewhere in a locked facility in Houston, 4 volunteers recently spent over a year sealed inside a box the size of a small apartment, pretending to live on a planet they never left. They ate food from a printer. They breathed air they had to monitor by hand. They spoke to their own families with a delay long enough to finish a cup of coffee before a reply came back. And they were only pretending. The real version of that experience is currently being planned in earnest, funded in billions, and sold to the public as the next great human adventure. This is why the actual daily reality of living on Mars deserves a much closer look than the postcard image most people carry around in their heads. Because underneath the red dust and the dramatic sunsets sits a set of physical facts that most space agencies mention only in footnotes, and those footnotes describe something closer to permanent life support triage than to any frontier humans have ever settled before. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. Picture the moment a future settler first steps outside a landed spacecraft, because that single moment tells you almost everything about what the rest of the story will look like. There is ground underfoot, rust colored and firm. There is a horizon, pale and strange, curving away in a way that feels almost familiar. And there is nothing else, because the sky above that horizon holds barely any air at all. The atmosphere on Mars carries roughly 0.6% of the pressure found at sea level on Earth. That is not thin air the way a mountain summit has thin air. It is closer to a vacuum than to anything a human body has ever been designed to tolerate unprotected. Physiologists have a name for the altitude on our own planet where this becomes deadly, a boundary called the Armstrong limit, sitting around 19 kilometers above sea level. Above that line, the pressure drops so low that water begins to boil at normal body temperature, not because anything got hot, but because there is no longer enough pressure pushing back to keep liquid water stable inside living tissue. The surface of Mars sits far beyond that limit every single hour of every single day. Step outside without a sealed and pressurized suit, and the moisture lining your eyes and your mouth would begin to boil away within seconds. Useful consciousness would last no more than about 15 seconds. Under 2 minutes later, it would be over. This has nothing to do with cold, and nothing to do with the composition of the air itself. It is simple physics, confirmed decades ago in altitude chambers built to keep pilots and astronauts alive. And even the little atmosphere Mars does have offers almost no comfort, because it is roughly 96% carbon dioxide, with only faint traces of oxygen mixed in. A human lung searching for breathable air on the Martian surface would find almost none, and would be poisoned by what little gas there is long before suffocation finished the job. So the first fact worth sitting with is this: nobody will ever simply live on Mars, the way that phrase is normally understood. A person can only ever live inside something on Mars, sealed away from the planet by an engineered shell that stands between a livable pressure and a hostile vacuum, every hour, without exception, for as long as they remain there. That shell is not a shelter you retreat to after a day outdoors, the way a tent or a cabin might function on Earth. It is the entire world. It is the only volume on an entire planet where a human body can function safely. And stepping outside its boundary without complete protection can end a life in less time than it takes to read this sentence aloud. Consider what that boundary actually has to withstand mechanically, because the pressure difference between the inside of a habitat and the Martian outdoors is enormous. If the interior is kept near Earth normal pressure, every square meter of wall is being pushed outward with a force equivalent to roughly 10 tons. Every seam, every window, Every airlock gasket is fighting to hold a livable bubble together against an environment trying constantly to tear it open. A crack no wider than a human hair can slowly bleed air out of a habitat over the course of hours. A larger breach could empty a room of breathable atmosphere before anyone had time to reach an emergency mask. Engineers who build spacecraft already understand how unforgiving this is. Even the orbiting space station, sitting in a controlled environment with a full mission control team monitoring it around the clock, has experienced small leaks that took specialists weeks to track down and seal. A Martian habitat would face the same physics, but with temperature swings of dozens of degrees between day and night working the seals loose, abrasive dust drifting into every joint, and a repair crew that does not exist because the nearest human beings capable of helping would be somewhere between 55 million and 400 million kilometers away, depending on where the two planets happen to sit in their orbits that year. A radio message sent home in a crisis would take between 4 and 24 minutes to arrive, one direction only. Any reply would take the same again. There is no such thing as calling for help on Mars, in any sense that word carries on Earth. There is only the crew, the tools they brought, and whatever spare parts happened to be packed months or years earlier by someone guessing at what might eventually break. Now think about how much room that shell would actually give a person to move around in. Most serious habitat designs studied by space agencies and private companies converge on something surprisingly small, somewhere in the range of a modest 2-bedroom apartment shared by a crew of 4. Except this apartment has no separate rooms for separate purposes in the way a home on Earth does. It holds the sleeping quarters, the kitchen, the exercise equipment, the medical bay, the laboratory, the food-growing racks, the water recycling machinery, the air processing units, and the workspace, all folded into the same tight footprint, for years at a time. There are no hallways leading anywhere else. There is no stepping outside for fresh air, because the air outside would end your life within moments. There is no walking over to visit a neighboring habitat without first suiting up, cycling through an airlock that takes real time to operate safely, crossing exposed ground while radiation and dust settle onto every surface of your suit, and then cycling through another airlock on the far side. Visiting the people next door becomes a full expedition, not a stroll. Inside that shell, daily life compresses down to a rhythm most people on Earth have never experienced. You eat in the same space where you work. You sleep within reach of the machinery, quietly keeping you breathing. You exercise in the same corner of the same room, looking at the same wall every single day, because there is nowhere else to exercise. The background hum of fans and pumps and compressors never stops, because true silence in that environment means something in the life support chain has failed. After the first few weeks, a person would know every scuff mark on every surface. After a few months, they would know the exact rhythm of every mechanical cycle running through the walls, the way a sailor learns the sounds of an old ship. The temperature outside that shell adds its own relentless pressure on the systems, trying to keep the interior livable. Average surface temperatures on Mars hover somewhere around -60 degrees Celsius. Near the equator, on a warm afternoon, readings might briefly climb toward freezing. Near the poles in winter, they can plunge past -120 degrees. Keeping a stable, comfortable interior against swings like that means heating systems running continuously, drawing power every hour of every day, with no season where the demand ever really eases. And even the wind, gentle as it feels in that thin atmosphere, carries something far more troublesome than force. It carries dust. Martian dust is extraordinarily fine, averaging only a few micrometers across, small enough to stay suspended in the thin atmosphere for weeks at a time, and small enough to slip deep into human lungs if it is ever inhaled. During the largest storms, which can grow to wrap around the entire planet and linger for months, that dust can block enough sunlight to cut solar power generation by more than 3/4. It is not simply gritty sand either. Samples studied from Martian rovers and from meteorites that fell to Earth show the dust contains fine silica, iron oxide, and a class of chlorine-based salts called perchlorates, toxic to the human body even in tiny concentrations. On Earth, drinking water contaminated with only a few parts per billion of these salts is enough to trigger a regulatory response. On Mars, they sit in nearly every handful of soil. Inhaling only a small amount of that dust could deliver more of these compounds than a person should safely absorb. And prolonged exposure to the fine silica alone can scar lung tissue permanently, a condition well documented in miners and industrial workers here on Earth. That dust does not politely stay outside either. Astronauts who walked on the moon during the Apollo missions discovered that lunar dust worked its way into everything, despite careful precautions, jamming mechanisms, scratching visors, and irritating throats after only a few days of exposure. Martian dust is finer still, and Mars has just enough atmosphere to keep that dust mobile and airborne in a way the airless moon never allowed. Every time an airlock cycles, every time a suit comes back inside, a small amount of that dust rides along with it. Filtration has to run constantly. Suits have to be cleaned as a serious daily task rather than an afterthought. And even with every precaution in place, trace amounts would slowly accumulate inside a sealed habitat over months and years, quietly raising the exposure risk for everyone living there. All of it invisible. All of it happening while the crew goes about an otherwise ordinary day. Going outside, then, is nothing like the free wandering shown in concept art and mission animations. A Martian surface suit would be a heavy, multi-layered, pressurized garment, weighing somewhere between 40 and 70 kilograms on Earth. Still a real physical burden even under the lighter Martian gravity. Putting one on and sealing it correctly takes real time, often close to an hour once every check is complete. Gloves thick enough to hold pressure, make fine hand movements, clumsy. The helmet visor limits how much of the world a person can actually see at once. And every excursion runs on a countdown, because the air supply inside that suit is finite, and the return trip to the airlock has to happen with margin to spare. Nobody wanders out to admire a sunset in a getup like that. They work against a clock, watching pressure and oxygen readings the entire time, because a torn glove seam or a jammed joint out on the open surface turns a routine task into a survival emergency within minutes. And here is something almost nobody considers about those brief excursions outside. Even while standing directly on the Martian surface, a person is never actually touching Mars in any sensory sense at all. The wind that stirs the dust is never felt on skin, because skin exposed to that wind would be exposed to a vacuum. The ground is never touched by bare hands, because bare hands would freeze and blister in seconds. Sound barely exists at all, because the atmosphere is too thin to carry anything beyond the faintest whisper to a human ear. Every dramatic photograph beamed back by rovers hides a landscape wrapped in something closer to true silence than anywhere on Earth, even the quietest desert or the deepest snowfield, because those places still have enough air to carry the murmur of their own wind. Every other frontier explorers have ever crossed on Earth still let them feel the place they had reached, cold biting at exposed skin, sand between fingers, salt spray on the lips. Mars denies that entirely. A person can travel farther than any human being has ever traveled to reach a place, and then spend their entire life there without once making direct, unmediated contact with the ground beneath their boots. As unforgiving as the pressure and the temperature and the dust are, none of them are the most dangerous thing about Mars, because none of them are invisible in quite the same way as what comes next. Earth sits inside two overlapping shields that almost nobody ever thinks about, because they have simply always been there. The first is a magnetic field generated deep inside the planet by a churning core of molten iron, extending far out into space and deflecting the great majority of charged particles arriving from the Sun and from deeper in the galaxy. The second is the atmosphere itself, a blanket of gas, roughly 100 kilometers thick, absorbing and scattering most of the high-energy radiation that slips past the magnetic field. Together, these two systems keep the radiation dose reaching the surface of Earth low enough that the human body barely notices it, repairing whatever small damage does occur without any conscious effort at all. Mars offers neither of these protections in any meaningful way. Its core cooled and solidified roughly 4 billion years ago, shutting down the internal engine that once generated a global magnetic field. A few weak patches of ancient magnetism remain frozen into the southern crust, but they cover only isolated regions and shield almost nothing. For all practical purposes, the entire planet stands magnetically unprotected against the particle environment of deep space. Its atmosphere, at under 1% the density of Earth's, does almost nothing to stop the most energetic particles either, which pass through it as if it barely exists. Instruments aboard the Curiosity rover have been measuring surface radiation continuously since it landed, and the readings confirm an annual dose from cosmic rays alone that runs roughly 80 to 100 times higher than the natural background radiation a person absorbs living on Earth. There is no way to turn that exposure off, and no hour of any day when it stops. Two distinct threats make up most of that danger, and both are more destructive to living tissue than most radiation encountered on Earth. The first is a constant rain of galactic cosmic rays, particles accelerated to extraordinary speeds by supernova explosions and other violent events across the galaxy, some of them heavy atomic nuclei stripped bare of their electrons. When one of these particles strikes a living cell, it does not simply pass through the way an ordinary X-ray does. It tears a dense track of damage straight through the molecular structure of the cell, shattering the bonds that hold DNA together. The body can repair a great deal of this damage, but not always correctly, and incorrectly repaired DNA is precisely how cancer begins. Because this radiation arrives constantly, rather than in occasional bursts, it simply accumulates, year after year, with no dose reduction available anywhere on the surface. The second threat arrives less often but hits far harder in short bursts. Sudden storms of energetic particles ejected from the sun during solar flares. A severe event of this kind can deliver, within a matter of hours, a dose large enough to cause acute radiation sickness in anyone caught unprotected on the surface, producing nausea, immune collapse, and in the worst cases, an outcome no medical kit on Mars could reverse. Earth's magnetic field deflects the overwhelming majority of this energy before it ever threatens anyone on the ground. Mars has no such deflection, and satellites orbiting the planet have directly observed these storms, stripping material away from its thin remaining atmosphere during major solar events. Space agencies place a career limit on how much radiation any single astronaut is allowed to absorb over their lifetime, calculated around an acceptable increase in long-term cancer risk. At the dose rates measured on the Martian surface, a person could reach that entire career limit in only a couple of years, and that number does not even include the months of exposure absorbed. Simply traveling there through open space, with none of the shielding a planetary atmosphere provides. Independent modeling using space agency risk calculations has suggested that radiation-related mortality and illness across a full Mars mission could climb into double-digit percentages under worst-case assumptions. And that figure does not yet account for possible damage to the nervous system from the heaviest particles, an effect scientists still do not fully understand, simply because nobody has ever been exposed to it for long enough to study. This is the reason almost every serious proposal for long-term Mars habitation eventually leads underground. Not as a dramatic choice, but as the only realistic way to bring that exposure down to survivable levels across years rather than months. Loose rock and soil piled above a habitat blocks a significant portion of incoming radiation. But the relationship between depth and protection is not as simple as more is always better. Research modeling radiation exposure at different depths beneath the Martian surface found something almost nobody expects: that the dose actually peaks a little below the surface rather than right at it. Because cosmic rays striking the soil produce a shower of secondary particles that scatter downward and sideways, briefly making a shallow burial more dangerous than standing in the open. Only once the covering material reaches roughly 1.5 to 2 meters thick does the dose drop down toward levels that would be considered acceptable for long careers back on Earth. Reaching 3 meters or more begins to approach something close to Earth's own natural background level. In practice, this means any habitat meant for permanent or long-duration use has to sit beneath a thick blanket of packed regolith or be built inside a natural cavity, offering equivalent protection. Orbital images of Mars have revealed what appear to be collapsed lava tubes, tunnels carved out by ancient volcanic flows, some of them wide enough to contain entire pressurized structures within their walls. The rock overhead in a tube like that could provide shielding without any construction at all, which has made these formations one of the more seriously discussed sites for early settlement. But their interiors remain completely unexplored. Their structural stability after billions of years of quiet decay is unknown. And reaching them at all may require navigating difficult terrain or carving entry points through solid rock. The alternative, building on the open surface and then piling meters of crushed stone over the top by hand or by machine, is a genuine construction project, requiring heavy equipment, reliable power, and months or years of preparation before any human being ever sets foot inside. Either path leads to the same conclusion. Long-term life on Mars does not happen beneath open sky, in a home with wide windows framing a Martian view. It happens beneath rock, in rooms with no natural light at all, because glass and thin polymer offer almost no protection against the particles that matter most, and every hour spent in a lightly shielded room quietly adds to a lifetime dose that can never be subtracted once it has been absorbed. Some engineers have proposed lining sleeping quarters with thick layers of water, an effective barrier against several forms of radiation, concentrating the heaviest protection exactly where a crew spends the largest share of their unconscious hours, while accepting somewhat higher exposure in workspaces used only briefly during the day. It is a compromise built entirely around rationing, a danger nobody can see, hear, or feel, tracked instead on a chart, the way a diabetic tracks blood sugar, because there is no other way to know it is happening at all. Every hostile environment on Earth still gives a person at least one thing for free. The Arctic offers breathable air. A submarine's reactor offers essentially unlimited power. Even the driest desert offers water somewhere beneath the sand, if a person is willing to dig deep enough. Mars offers nothing at all. Every single input the human body requires to stay alive has to be manufactured, recycled, or extracted by machine, running continuously, with no natural source anywhere on the surface that a person could simply reach out and use. Begin with oxygen, because without it, every other problem on this list becomes irrelevant within minutes. The Martian atmosphere is almost entirely carbon dioxide, with only the faintest trace of breathable oxygen mixed in, far too little to filter out directly. Producing usable oxygen means breaking the chemical bonds holding it inside other molecules, either by splitting water into hydrogen and oxygen using electrical current, or by splitting the abundant carbon dioxide in the air itself. A small experimental device flown aboard the Perseverance rover successfully demonstrated this second method directly on the Martian surface, proving the chemistry works. But the amount it produced was tiny compared to what a small crew would actually need every single day. And scaling that process up to something dozens of times larger is not simply a matter of building a bigger box. Larger systems demand far more power, generate more waste heat that has to be managed, and introduce more components that can fail in an environment with no replacement parts on hand. And oxygen generation is not something that can be run for a few hours and then paused. If it stops for even a single day, with a full crew breathing inside a sealed space, carbon dioxide levels begin climbing toward dangerous territory, while oxygen levels fall toward the point where clear thinking becomes difficult, which is precisely the symptom least likely to be noticed by the person experiencing it. Removing that exhaled carbon dioxide is its own continuous task, running in parallel, every hour, because 4 people breathing inside a sealed room produce a steady stream of it that has to be scrubbed from the air before it accumulates to harmful levels. Humidity has to be pulled out of the air as well, because moisture from breathing, cooking, and simple human presence builds up quickly in a closed volume, and left unchecked, it fogs equipment, corrodes wiring, and creates ideal conditions for mold. None of this runs itself. Every part of what a person on Earth thinks of simply as air has to be actively built, moment by moment, by machinery that a small crew is entirely responsible for keeping alive. Water follows a similar pattern. An adult needs several liters a day for drinking alone, and considerably more once cooking, hygiene, and crop irrigation are added in. Orbital surveys and rover measurements have confirmed that Mars does hold water, mostly locked away as ice beneath the surface at higher latitudes, buried under anywhere from a shallow covering to several meters of soil. Reaching it means excavating through frozen, compacted ground in extreme cold, melting what is recovered, and then filtering out the same toxic perchlorate salts found throughout Martian dust before the water becomes safe to drink or grow food with. Every one of those steps demands power and machinery that has to keep functioning reliably in an environment actively working to degrade it. Once purified, that water enters a closed recycling loop that has to run with near-perfect reliability, because a habitat this small has no reserve large enough to absorb weeks of failure. Systems on the orbiting space station that perform a similar function have needed regular hands-on maintenance, even with a full supply chain from Earth supporting them. On Mars, the same kind of malfunction has to be diagnosed and repaired using only whatever tools and spare parts happen to already be on site, and the cost of prolonged failure is not discomfort. It is dehydration setting in within days. Feeding a crew presents a problem shipping alone cannot solve, because the mass of food required for even a handful of people over several years would be enormous, and no early mission architecture can afford to keep sending that much weight across interplanetary space indefinitely. Growing food locally is not a nice ambition for a Mars settlement. It is an absolute requirement for anything beyond a short stay. And growing food on Mars means growing it entirely indoors, under artificial light, inside pressurized and climate-controlled modules, because the sunlight reaching the surface is weaker than on Earth and passes through an atmosphere too thin to hold any warmth. Martian soil cannot simply be planted in either. The same perchlorate salts poisoning the dust would poison anything grown directly in it. And the soil lacks the organic material and microbial life that healthy farmland on Earth depends on. Before it could support a single crop, it would need extensive washing to remove the toxic salts, followed by careful supplementation with nutrients and beneficial microbes, an entire industrial process just to make dirt usable. Most realistic designs skip native soil altogether, growing crops instead in water-based systems where nutrients are delivered directly to the roots under banks of tuned lighting. Crop selection would be narrow by necessity, favoring fast-growing, calorie-dense plants like potatoes, wheat, soybeans, and leafy greens. Because anything less efficient wastes power and space a small habitat cannot spare. Meaningful amounts of animal protein would be essentially out of reach, since raising livestock costs vastly more in feed, water, and space per calorie than growing plants directly, meaning a Mars settlement would almost certainly eat a vegetarian diet, not by philosophy, but by hard resource math. And unlike a failed harvest on Earth, which simply means importing food from somewhere else, a failed crop cycle on Mars has nowhere else to draw from. A lighting failure, a contamination event, or a miscalculated nutrient mix could wipe out weeks of food production in a single incident, with reserves that are finite and only slowly rebuilt. Waste has to be managed just as carefully, because in a sealed habitat, nothing simply disappears the way it does on Earth. Urine feeds back into the water recycling system. Solid waste has to be dried, treated, and either stored or broken down for potential reuse. Packaging, worn filters, and damaged equipment all have to be accounted for and stored somewhere inside a space that was never designed to hold years of accumulated debris, because there is no landfill anywhere on the planet to send it to. Underneath every single one of these systems sits the question of power, because oxygen generation, water recycling, food production, heating, lighting, filtration, and every instrument in the habitat all draw from the same electrical supply, and none of them can run without it. Solar panels are the most obvious energy source, since sunlight still reaches the surface even at a reduced strength, but they come with real limitations. Martian days run roughly as long as Earth days, meaning panels only generate power for about half of every rotation, with batteries needed to cover the rest. And as already established, the dust storms capable of wrapping around the entire planet can cut solar output by a large majority for weeks at a stretch, arriving at precisely the moments when heating demand is highest. Because storms also drag surface temperatures down further. Small nuclear power units offer an alternative that keeps generating electricity regardless of dust, darkness, or season. And early prototype reactors have already been tested successfully at a small scale. Scaling that technology up to the output a full habitat would need remains an active engineering challenge, and nuclear systems bring their own weight, their own shielding requirements, and their own failure risks in an environment where a malfunction cannot simply be evacuated from. Most realistic plans combine both approaches: solar arrays for routine daytime use, batteries to bridge the night, and one or more reactors providing a steady baseline regardless of weather. That redundancy is essential for survival, and it is also expensive in every currency that matters off-world. Mass that has to be launched, volume that has to be found inside an already cramped habitat, and maintenance hours that have to come from a crew whose schedule is already full. On Earth, an entire invisible network quietly supports daily life without anyone thinking about it. A power grid delivering electricity, a treatment plant delivering clean water, A supply chain delivering groceries, specialists arriving within hours whenever something breaks. People are so deeply embedded in that support system that they forget it exists at all. On Mars, every part of that network sits inside the walls of a single habitat, and the specialist who repairs it is whoever happens to be living there. There is no grid to fall back on, no supply chain to call, no technician who can simply drive over. Every pump, every valve, every filter, every seal, every circuit board in that habitat is something the crew has to understand deeply enough to diagnose and fix themselves. Imagine an ordinary morning to see what that actually looks like in practice. A person wakes under artificial light tuned to mimic a sunrise that will never actually reach their room because their sleeping quarters sit beneath a meter or more of packed regolith for radiation protection. Before breakfast, they check the air quality panel, oxygen level, carbon dioxide level, humidity, pressure, and trace contaminants. One of the scrubbers is drawing slightly more power than usual, which could mean nothing, or could mean a fan bearing beginning to fail. They log it and move on. They check the water system, filter pressure creeping upward, another item added to today's list. They check the crop racks, and notice a couple of plants showing the first faint signs of a nutrient deficiency, adjusting the feed accordingly. They check yesterday's solar output, down slightly from dust, settling on the panels overnight, meaning somebody needs to go clean them today. They check the week's radiation log, still within budget, but worth watching. All of that happens before the first meal of the day. A simple rehydrated grain dish and a small serving of greenhouse greens, largely the same meal eaten yesterday, because the crop rotation only produces real variety slowly over weeks. None of this is a bad morning. This is an ordinary one. A bad morning is the one where 2 or 3 of those readings land in the danger zone at once, and a decision has to be made about which failing system gets addressed first, while the others simply wait. A serious dust storm rolling in can turn this into a genuine crisis within hours. Solar output dropping sharply, batteries draining faster than expected, non-essential systems shut down one by one to conserve power, while heating and air and oxygen generation stay running no matter what because they cannot be paused. If a water pump seal happens to fail during that same storm, worn down by mineral buildup that has been slowly accumulating for months, the crew now has 2 emergencies competing for the same limited hands and the same limited hours. That is not a disaster movie plot. That is a plausible, ordinary week, because the planet rarely attacks with one dramatic event. Instead, it wears away at the margins through dozens of small, simultaneous stresses that each look manageable alone, but together consume every spare hour a small crew has. Studies of crew time aboard the orbiting space station show that even there, with a full supply chain and expert ground support just a radio call away, astronauts spend close to half their working hours on maintenance and housekeeping, rather than the science or exploration that brought them there in the first place. On Mars, with a longer communication delay, scarcer spare parts, and a harsher environment degrading everything faster, that share would likely be even higher. A Mars crew, in other words, would not be explorers who occasionally stop to fix something. They would be maintenance technicians who occasionally find time to explore. Everything covered so far belongs to the category of engineering, meaning it can, at least in theory, be solved with enough time, money, and clever design. Pressure vessels can be strengthened, shielding can be thickened, oxygen systems can be scaled up, power sources can be made redundant. But there is one variable that no amount of engineering can fully compensate for, because it lives inside the human body itself, rather than inside the walls of the habitat. That variable is gravity, and Mars offers only about 38% of what a person's body evolved to expect on Earth. Every bone, every muscle, every blood vessel in the human body developed under a specific gravitational load, and Mars simply does not provide it. Decades of research aboard the orbiting space station have documented what happens to the human body in weightlessness with painful clarity. Bone density and weight bearing, areas like the hips and spine, can decline by roughly 1 to 2% every single month. Muscle mass shrinks, particularly in the legs and lower back, even with hours of daily resistance exercise built into the schedule. The heart, no longer working against gravity to push blood upward, gradually grows weaker. Bodily fluids shift toward the head, raising pressure inside the skull in a way that has measurably damaged the eyesight of some long-duration astronauts. All of that has been studied extensively at zero gravity. What happens specifically at Martian gravity is a far bigger unknown, because almost nobody in history has ever lived at that specific gravitational level for more than a few days. Recent animal research offers a hint rather than an answer. Experiments exposing mice to gravity levels close to that of Mars aboard the orbiting space station found that this partial gravity slowed muscle loss compared to full weightlessness, but did not stop it completely, with full protection only appearing at a gravity level closer to 2/3 of Earth's. Separate laboratory research studying bone-forming cells under simulated Martian gravity found their activity significantly reduced, and interestingly, not dramatically better than what was observed at much lower gravity levels, suggesting that even a moderate reduction below Earth normal may be enough to disrupt the basic process of maintaining healthy bone. If that finding holds true in real human bodies, it would mean Mars gravity offers meaningfully less protection than its numeric value alone might suggest. Slowing the decline, perhaps, but very likely not stopping it, month after month, year after year, with no way to simply dial gravity back up to fix it. That matters beyond simple fragility, because bone marrow also manufactures blood cells, meaning chronic bone loss can weaken immune function and reduce the blood's ability to carry oxygen, compounding problems already caused by chronic radiation exposure. Cardiovascular changes over years at partial gravity remain entirely untested in humans, and the same is true for the long-term effects of a slightly elevated pressure inside the skull, an issue already linked to vision problems in astronauts who spent extended time in full weightlessness. Now extend this uncertainty a generation further, because a genuinely permanent settlement eventually means children. No mammal in recorded history has ever been conceived, carried to term, born, or raised its entire life under partial gravity. Nobody knows whether a developing skeleton would form correctly under these conditions, whether the inner ear systems responsible for balance and a great deal of early brain development would mature normally, or whether a child raised entirely on Mars could ever physically tolerate a trip back to Earth, where gravity would suddenly be well over 2.5 times everything their body had ever known. A child born and raised there might be permanently bound to that world, not through any choice, but through simple biology. Their skeleton and cardiovascular system shaped from birth by a planet they might never be able to safely leave. And this uncertainty is not limited to children. Even a healthy adult who arrives from Earth and spends years living under Martian gravity would gradually adapt to it, bones thinning, muscles weakening, a cardiovascular system recalibrating downward to match a lighter load. After enough years, returning home would mean asking a body that has quietly adjusted to a fraction of Earth's gravity to suddenly bear the full weight of it again, with landing forces alone risking fractures in a weakened skeleton, and a deconditioned heart potentially struggling to keep blood flowing to the brain while simply standing upright. Settlement on Mars may end up being closer to a one-way commitment, not because no rocket exists to bring people home, but because after enough time, The body itself quietly crosses a line past which returning becomes genuinely dangerous. Set the body aside for a moment, because the mind faces a burden of its own, one that may end up being harder to solve than any piece of hardware discussed so far. Space agencies have already run extended simulations here on Earth to study exactly this question, sealing small volunteer crews inside mock habitats built to mimic the size, isolation, and communication delays of an actual Mars mission for over a year at a time. Volunteers coming out of these experiments consistently report something that sounds almost too simple to matter, and yet clearly does. They miss green grass. They miss open sky. They miss the feeling of natural wind on their skin. These are not luxuries in any trivial sense, because the human nervous system did not evolve inside sealed metal rooms. It evolved beneath open horizons filled with shifting light, moving air, and the quiet, constant sensory richness of a living world. And decades of research into human psychology confirm that even brief access to natural surroundings measurably lowers stress and sharpens the mind, while prolonged confinement in small, unchanging, artificially lit spaces produces the opposite: disrupted sleep, rising irritability, and a slow, emotional flattening that researchers studying isolated missions have come to recognize as a recurring pattern, often showing up hardest somewhere in the back half of a long mission, once the initial adrenaline has faded and the return date still feels far away. On Earth, every one of these simulations carries a quiet safety valve running beneath the surface, because the volunteers know, even if they rarely say it aloud, that the experiment will end, and that green grass and open sky are still waiting for them outside the facility doors. On Mars, that safety valve simply does not exist. There is no walking outside without a sealed suit, ever. There is no genuine blue sky, ever. There is no living landscape beyond the reinforced viewport, ever. Only the same tightly framed patch of red plain, day after day, year after year. Even light itself becomes a subtle adversary in a habitat buried beneath meters of rock for radiation protection, because there is no true sunrise warming the walls. No gradual shift from morning blue to evening amber, only artificial lighting tuned largely for growing crops rather than regulating a human sleep cycle. And research on submarine crews and polar research teams consistently shows that living for long stretches without genuine daylight cues disrupts sleep and mood in ways that circadian lighting systems can soften but never fully replace, because some part of the human brain seems to recognize the difference even when the conscious mind does not. A landmark 520-day isolation experiment conducted in Moscow years ago, simulating a full Mars mission from launch to return, recorded real behavioral shifts in its crew of 6 over that time: disrupted sleep patterns, reduced activity, measurable changes in stress hormones, and genuine interpersonal friction that had to be managed through deliberate communication protocols. That experiment lasted a little over a year and a half. An actual Mars settlement would mean decades, watching the same handful of faces every day for the rest of a person's working life, because there are only ever a few other humans within tens of millions of kilometers, and there is no door in the entire habitat that leads anywhere but another room inside the same sealed structure. Authority itself becomes an open question in that kind of isolation, because a small crew has to decide for itself who rations power during a storm, who repairs which system first when 2 fail at once, and what happens if someone begins showing real signs of struggling under the weight of it all, with no outside referee available to step in and settle a dispute in real time. Communication with Earth compounds all of this, because depending on where the 2 planets sit in their orbits, A message can take anywhere from roughly 4 to 24 minutes to arrive one way, meaning a genuine back-and-forth conversation, in the sense most people understand that word, becomes physically impossible. Every exchange with family and friends turns into something closer to trading recorded letters than having a conversation. Each message carrying the emotional weight of distance stretched out over time, and over months and years, Earth itself can start to feel less like home and more like a distant idea, while the small crew inside the habitat slowly becomes its own tightly bound world, shaped entirely by shared confinement rather than by anything left behind. Given all of this, some measure of depression across a multi-year mission becomes less of a personal failing and more of a predictable outcome. A natural response of a brain evolved to need a certain baseline of novelty and open space, deprived of both for years at a stretch, with medication supplies finite and real-time therapy from Earth simply impossible given the delay. Medical care on Mars would rest almost entirely on a single small cabinet, and whoever among the crew happened to be trained to use it. That cabinet might hold a limited supply of medication, basic surgical tools, and a compact imaging device, but nothing resembling a real operating theater, a blood bank, or a specialist who has spent an entire career treating one specific condition. An infection, a broken bone, a burst appendix, any of these could likely be managed with whatever the habitat happens to have on hand. But anything beyond that, a condition requiring true surgery, an aggressive illness, a severe traumatic injury, would very likely be untreatable, because evacuation back to Earth takes months under the best possible alignment of the two planets, and is simply impossible the rest of the time. A condition that any emergency room on Earth could resolve in a single afternoon could become life-threatening on Mars, purely because of distance rather than severity. That knowledge sits quietly beneath every ordinary task inside the habitat, turning a simple climb up a ladder to fix a ventilation duct into something carrying a sliver of real risk, because a fall, resulting in a fracture that cannot be properly treated, is a genuine possibility, not a dramatic exaggeration. There is another layer to this story that rarely gets discussed, and it has to do with how deceptively familiar the Martian landscape looks in every photograph sent home. Mars is often described as Earth-like because it has mountains, canyons, and what appear to be dry riverbeds carved long ago by flowing water. Olympus Mons, the largest volcano anywhere in the solar system, rises roughly 22 kilometers above the surrounding plain, nearly 3 times the height of the tallest mountain on Earth. Valles Marineris, a canyon system stretching for thousands of kilometers, plunges several kilometers deep in places, dwarfing the Grand Canyon in almost every dimension. These features look, at first glance, like Earth geology simply scaled up, and that visual familiarity is exactly what makes the planet so quietly deceptive. The mountains hold no breathable air at any altitude. The canyons hold no flowing water. The dry channels have been empty for billions of years. Mars looks like a desert a person could survive in with the right preparation, the way explorers have survived deserts on Earth for centuries. It is, in reality, a vacuum chamber shaped like a desert, and no amount of visual familiarity changes the physics waiting just beyond the habitat wall. People studying photographs from rovers naturally process them through an Earth-shaped lens, seeing rocky terrain that resembles a canyon in the American Southwest, watching small dust devils spin across the plain exactly the way they do back home, and concluding, almost without realizing it, that the environment must be harsh but ultimately survivable, the way a very cold desert or a high mountain plateau is survivable. It is not. No desert on Earth, no mountain summit, no polar ice sheet comes remotely close to the hostility sitting just outside a Martian viewport. The driest patch of the Atacama Desert still has breathable air. The summit of the tallest mountain on Earth still holds enough pressure to keep blood liquid inside the body. The coldest Antarctic winter still sits beneath a functioning magnetic field and an ozone layer blocking the worst of the sun's radiation. Mars has none of these things, not even in a weakened form, and the view through the viewport that most people imagine when they picture living there, a red horizon stretching endlessly into the distance, would rarely, if ever, be the daily experience of anyone actually living inside a shielded habitat. Large windows represent structural weak points in a pressurized shell and offer almost no protection against the radiation constantly passing through the sky above. The real daily view would most often be a small reinforced port, or simply a camera feed on a screen, because the interior of a machine is safer than a room built around glass. The dust storms deserve a closer look on their own, because they reveal exactly how quickly a manageable situation can turn into a genuine emergency on a planet with no outside help available. In a well-documented event years ago, a global dust storm swept across the entire surface of Mars and persisted for weeks, thick enough to plunge the sky into a dim, hazy twilight even at midday. A solar-powered rover that had already been exploring the surface for close to 15 years, far longer than anyone originally expected it to survive, lost power as dust settled thickly across its panels, and it never woke up again. That rover had no biological needs, no need to breathe, no need to stay warm, no crew depending on it for survival. A human settlement facing the same storm would be watching its oxygen generation slow, its heating strain against dropping temperatures, and its water recycling falter, all at once, while the same storm coating the solar panels also blocks the sunlight needed to recharge the batteries meant to compensate for it. Cleaning those panels becomes a serious, physically demanding task performed in a bulky, pressurized suit, timed against a shrinking air supply, and repeated again and again for as long as the storm continues, because the dust never really stops settling as long as it stays suspended in the atmosphere. Backup power sources, not dependent on sunlight, would ease this particular danger considerably, but they add their own weight, their own shielding requirements, and their own failure risks to a system that already has more moving parts than any small crew can fully monitor at once. What makes Mars so uniquely unforgiving is not any single hazard on its own, but the way every hazard quietly reinforces the others, creating problems that cannot really be solved in isolation. Radiation forces the crew underground, or behind meters of packed rock, but dust follows them inside anyway, because there is no airlock protocol thorough enough to keep every last particle out over months and years of regular use. The suits meant to protect against vacuum and cold also serve as the main vehicle, carrying that dust back inside every single time someone returns from an excursion. The solar panels meant to power the air filtration systems are the exact same panels a dust storm coats and disables, at precisely the moment clean, filtered air matters most. The heating systems meant to fight off the deadly cold outside are the same systems drawing hardest on a power supply already strained by that same storm. Every mitigation strategy for one danger quietly creates a new dependency on, or vulnerability to, another. And this compounding is what separates Mars from every hostile environment humans have ever occupied on Earth. In Antarctica, the cold is severe, but the air remains breathable and radiation levels stay low. Aboard a submarine, the confinement is extreme, but the hull holds back ordinary seawater pressure rather than a near-total vacuum, and there is no toxic dust drifting through the corridors. Deep inside a mine, the dust can be genuinely dangerous. But a worker can still walk out at the end of a shift and breathe clean air under open sky. On Mars, every major hazard runs simultaneously, all the time, reinforcing every other one, with no dimension of the environment where a person can simply exist without some form of active mechanical intervention holding the danger back. This compounding also shows up in the sheer difficulty of keeping the habitat supplied with what it needs to keep functioning. Every spare part not already stored on site has to be shipped from Earth at enormous cost, or manufactured locally using raw Martian materials, a manufacturing capability still very much in its early stages of development. Three-dimensional printing using local regolith or recycled plastic could eventually produce some basic replacement parts, but the range of materials achievable this way remains limited for the foreseeable future, and certain items simply cannot be improvised from raw dirt and scrap. Precision sensors, delicate seals meant to hold pressure, sensitive electronic components, specialized medical equipment. These have to be anticipated, packed, and delivered months or years ahead of when they might actually be needed, based on predictions about what will eventually wear out or break, predictions that will inevitably sometimes turn out to be wrong. If something fails that nobody anticipated, or if the one spare on hand was already used for an earlier repair, the crew faces a genuine supply gap that cannot be closed for years. And improvisation stops being an occasional point of pride the way it has been in a handful of famous moments throughout space history, and instead becomes a routine, exhausting requirement of daily survival. Every crew member effectively has to become part plumber, part electrician, part chemist, part mechanic, and part systems engineer, because there simply is nobody else to call. Consider what an actual conversation with someone back on Earth would feel like after a year or two of this. A parent speaking to a child, a partner speaking to the person they left behind, would never experience anything resembling a normal phone call, because the delay alone rules it out. A message sent home might take anywhere from several minutes to nearly half an hour to arrive, one direction only, meaning a simple back-and-forth exchange, the kind that takes seconds on Earth, could stretch out over the better part of an hour. Video calls, in the sense most people understand them, become physically impossible, replaced instead by something closer to recorded letters. A message sent. A reply that arrives sometime later, carrying all the emotional weight of distance stretched across time rather than compressed into a live conversation. Birthdays would be recorded and sent rather than shared. News from home, a promotion, an illness, the arrival of a grandchild, would arrive on a delay long enough that by the time it reached the habitat, the moment being described would already belong to the past. Over months and years, this steady drip of delayed, second-hand information changes the emotional shape of a relationship, not through any single dramatic rupture, but through countless small moments of feeling slightly behind, slightly outside, slightly disconnected from the rhythm of a life still unfolding back on a planet growing further away with every passing week. Researchers who study isolated communities, from polar research stations to long submarine deployments to remote military postings, have consistently observed a kind of social drift in groups cut off from home for extended periods, where the isolated group gradually identifies less with the culture it left behind and more with the small, tightly bound community sharing its immediate daily reality. On Mars, that drift would likely deepen rather than fade, because unlike every one of those Earth-bound postings, there is no scheduled rotation, home waiting at a fixed date on the calendar, no return flight already booked, nothing pulling attention back toward the life that used to exist somewhere else. The people inside the habitat would slowly become each other's entire social world, for better and for worse, sharing every meal, every disagreement, Every small victory and every quiet frustration, for years on end, with nowhere else to go and no one else to talk to. Return now to the question of children, because it deserves more than a passing mention, given how directly it exposes the gap between the romantic version of Mars settlement and the version biology actually allows. If humans genuinely intend to settle Mars rather than simply visit it, reproduction eventually becomes unavoidable. And right now, there is no meaningful data to answer even the most basic questions surrounding it. Nobody knows whether a human fetus could develop normally under a gravitational pull, barely a third of what every previous generation of humans developed under. Nobody knows whether the fluid systems responsible for balance, developing early inside the inner ear, would mature correctly without the gravitational reference point they evolved around. Nobody knows whether a skeleton built from birth under partial gravity would end up structurally different in ways that matter. Lighter, more fragile. Shaped by a mechanical environment unlike anything the human body has experienced across its entire evolutionary history. Answering these questions would require, quite literally, testing them on real children, born into an environment nobody could remove them from if something went wrong, with no control group anywhere in the solar system experiencing the same conditions for comparison, and no way to simply relocate a child to Earth gravity if early development seemed to be going poorly. This is not a minor footnote to the dream of settling another planet. It sits at the very center of what settlement actually means, because a colony that cannot safely reproduce is not a colony in any lasting sense. It is a rotating outpost of people who arrived from somewhere else, and any serious plan for a permanent human presence on Mars eventually has to reckon honestly with a question that current science simply cannot answer yet, no matter how confidently it gets glossed over in promotional material. Strip away the engineering and the physiology for a moment, and simply picture what an ordinary evening would feel like at the end of one of these days. Dinner would likely be some rotation of the same handful of dishes built around whatever the hydroponic racks happen to be producing that week. Potatoes prepared a slightly different way than the night before. A small side of greens, a protein substitute reconstituted from stored supplies. Eaten in the same room used for work earlier that day. At the same table, with the same 3 or 4 people who were there for breakfast and lunch as well. Entertainment would be limited to whatever digital libraries had been loaded before departure, since streaming anything new from Earth in real time is impossible given the delay, meaning favorite shows, books, and music would eventually all be watched, read, and listened to more than once. The well of genuine novelty slowly running dry over months and years, in a way it never does, on a planet full of billions of other people, constantly creating something new. Exercise would happen on the same equipment, in the same corner, at roughly the same time, because bone and muscle loss under partial gravity makes daily physical effort a medical necessity rather than an optional lifestyle choice. 2 hours or more some days, logged and tracked the way medication doses are tracked, not because anyone particularly enjoys it, but because skipping it accelerates a decline nobody wants accelerated. Small pleasures would matter enormously in an environment like this, precisely because there are so few of them. A successful harvest of something slightly different than usual. A message from home that happened to arrive with good news attached. A quiet hour with nothing urgent flashing on any panel. These small moments would likely carry outsized emotional weight, the way a warm afternoon carries outsized weight for someone who has spent an entire winter indoors, except on Mars. The entire year is winter, in every sense that matters, and there is no spring on the other side of it, only the next storm, the next repair, the next small mercy worth noticing. None of this is meant to suggest that human beings should never attempt it, because history offers a fairly consistent answer to the question of whether difficulty alone has ever stopped this species from reaching towards something new. Sailors once crossed oceans in wooden ships so poorly equipped that a significant share of any given crew never made it back, driven by trade routes, curiosity, or simple restlessness rather than any guarantee of survival. Climbers have summited peaks that offer nothing at the top beyond thin air and a view, accepting frostbite, exhaustion, and real risk of not coming down again, purely for the experience of standing somewhere few others ever had. Explorers walked into deserts with barely enough water to survive the crossing, sailed directly into storms, descended into caves with no real understanding of what waited below, and eventually strapped themselves into vehicles designed to launch them off the planet entirely, sitting atop a controlled explosion with a real chance the whole thing might fail catastrophically. None of these choices were rational in the narrow, risk-minimizing sense of the word, and none of them needed to be, because something in human behavior has always pushed toward the edge of the known world, regardless of the cost, simply to find out what waits on the other side of it. Mars is the next edge, and the honest case for going is not that it will be comfortable, or that it will resemble any previous form of settlement in human history, but that the impulse driving people toward it is the same impulse that has driven every difficult expedition this species has ever undertaken, and that impulse rarely waits around for perfect conditions before acting. What matters most, though, is that anyone who eventually goes should go with total clarity about what they are actually choosing, not the version sold in artist renderings and promotional footage, but the version grounded in the physics, chemistry, and biology already well understood today. They should go knowing daily life will resemble operating a submarine far more than homesteading on any frontier this planet has ever offered. They should go knowing their bodies will change in ways medicine cannot fully predict, and their minds will be tested in ways no simulation on Earth can fully prepare them for. They should go understanding that the connection back to everyone they love will thin out over time into a slow trickle of delayed messages crossing an ever-widening gap, and that after enough years, their own body may quietly close the door on ever safely returning, not because the technology to bring them home does not exist, but because their bones and their heart will have adapted to a world that no longer lets them leave it behind. Before any of this even becomes relevant, there is the small matter of surviving the trip itself, something easy to forget while focused entirely on life inside a habitat that has not been reached yet. Depending on the alignment of the two planets and the amount of fuel a mission is willing to spend, the journey from Earth to Mars takes somewhere between roughly 6 and 9 months, spent almost entirely inside a spacecraft not meaningfully larger than the habitat waiting at the other end. For that entire stretch, the crew floats in weightlessness, already losing bone density and muscle mass before they ever set foot on the surface, already absorbing a steady dose of the same cosmic radiation described earlier, except now with none of even the thin protection Mars eventually offers once they land. There is no possibility of turning back partway through. Once the spacecraft commits to its trajectory, the crew is fully isolated from Earth for the length of the journey, dependent entirely on the same kind of closed-loop life support systems that will define the rest of their lives on the surface, except now confined to an even smaller volume, with even less room to escape each other, and even less margin for error if something breaks. By the time the spacecraft finally reaches Mars and begins its descent, a sequence that has to happen with almost no room for mistakes, given the thin atmosphere offering far less braking assistance than a spacecraft would get returning to Earth. The crew has already spent the better part of a year adapting to weightlessness, and now has to adapt immediately to a new, different, and equally unfamiliar gravitational environment, all while running on limited sleep and the accumulated fatigue of a journey that offered no true rest the entire way. The arrival itself, in other words, is not a triumphant final step after the hard part is over. It is the moment the hard part truly begins, layered directly on top of months of physical decline nobody gets to recover from before the real work of staying alive on the surface even starts. Once settled into the habitat, questions of authority and governance become unavoidable in a way most people back on Earth never have to think about. Somebody has to decide how power gets rationed during a storm, which repair takes priority when two systems fail on the same day, and what happens if a crew member begins showing real signs of struggling under the psychological weight of it all, unable to safely continue certain duties. Aboard the orbiting space station, mission control on Earth provides a layer of outside authority, arbitrating disagreements and offering guidance grounded in a broader perspective than anyone inside the vehicle can maintain on their own. On Mars, with a communication delay stretching up to nearly half an hour each direction, real-time arbitration from Earth is simply not possible. Whatever authority exists has to live inside the habitat itself, whether that means a designated commander with final say, a consensus-based system requiring agreement among the full crew, or some hybrid arrangement worked out in advance and tested only in theory before departure. Every one of these arrangements carries real risk, because a small, isolated group making high-stakes decisions with no outside check, no court to appeal to, and no possibility of simply leaving if the process breaks down, represents a kind of self-governance no analog mission on Earth has ever truly tested. Since even the most realistic simulations still operate under the implicit authority of the space agency running them, and the legal system of whatever country hosts the facility, Mars offers no such backstop. Whatever structure the crew builds for itself becomes, in practice, the only law that exists for tens of millions of kilometers in any direction, and the quality of the relationships inside that habitat may end up mattering as much to long-term survival as any single piece of engineering discussed so far. The people selected for a mission like this would almost certainly go through years of preparation before ever boarding a spacecraft, chosen not just for technical skill but for psychological resilience, the ability to remain calm and functional under sustained, compounding stress with no possibility of removal from the situation until the mission itself ends, if it ever does. Training would need to cover an extraordinary range of disciplines at once: basic surgery and emergency medicine, plumbing and electrical repair, greenhouse agriculture, chemistry, atmospheric systems, and enough engineering knowledge to diagnose failures in equipment none of them personally designed. Even with the best selection process available, no amount of screening on Earth can fully predict how a specific human mind will hold up after 3, 5, or 10 years inside the same sealed rooms with the same small group of people, because nothing in Earthbound analog testing quite replicates the psychological weight of knowing that return is either impossible or medically dangerous, that every mistake carries real consequences with no outside safety net, and that the isolation is not scheduled to end on a fixed date printed on a calendar somewhere back home. What seems to matter most in every isolated mission studied so far, from polar expeditions to submarine deployments to the analog Mars simulations already run on Earth, is not simply toughness or technical competence, but a strong, deeply internalized sense of purpose, something that gives the daily grind of maintenance and repair genuine meaning beyond mere survival. Crews that frame their work as contributing to something larger than themselves. A scientific mission, a step toward a genuinely permanent human presence beyond Earth, tend to weather isolation better than those focused purely on getting through each individual day. This suggests that, Psychological survival on Mars may depend as much on the story a crew tells itself about why it is there, as on any medication or therapy protocol packed into the medical bay. A strange but consistent finding across nearly every extreme environment humans have voluntarily entered. Building the physical structures a crew depends on presents its own extended challenge, since almost nothing about permanent construction on Mars resembles construction on Earth. Concrete, as it is normally made, requires water in quantities a Mars settlement can rarely spare, and traditional building materials are simply not available locally in any usable form. Researchers have experimented instead with regolith-based building materials, mixing crushed Martian soil simulant with binding agents to produce bricks or panels strong enough for basic structural use. And with three-dimensional printing techniques that could, in principle, allow robotic systems to construct simple shelters layer by layer using local material before any human crew ever arrives, reducing the mass that has to be launched from Earth. Early tests of these techniques remain promising but limited, since regolith-based materials tend to be more brittle than conventional concrete, and the extreme temperature swings between day and night place real stress on any structure, not specifically engineered to expand and contract repeatedly without cracking. The most realistic near-term approach likely combines a small number of pressurized modules launched directly from Earth, engineered and tested extensively before ever leaving the ground, with locally sourced regolith piled on top purely for radiation shielding, rather than relying on fully local construction for anything that actually has to hold pressure against a near vacuum. Even simple tasks like moving that regolith into place become substantial engineering projects of their own, requiring excavation equipment that can function reliably in extreme cold, thin atmosphere, and constant abrasive dust. Equipment that itself has to be shipped from Earth long before any human presence begins, and operated autonomously or semi-autonomously for months at a time before a crew ever sets foot on the surface to inhabit what has been prepared for them. The greenhouse modules, cramped and purely functional as they are, would likely become one of the most psychologically important spaces inside the entire habitat, not simply because they produce food, but because they are the only room where anything is actually alive and visibly growing. Every other surface inside the habitat is metal, plastic, or screen, unchanging from one day to the next, except when something breaks. The greenhouse alone offers green leaves, the smell of damp soil substitute in growing plants, and the small, quiet satisfaction of watching something develop over time rather than simply monitoring it for failure. Analog mission volunteers and researchers studying isolated environments consistently note that crew members gravitate toward these growing spaces far more than strict nutritional necessity would. Explain, spending extra unscheduled time there, tending plants that do not strictly need the extra attention, because the simple presence of living, growing things appears to meet some psychological need that no amount of screen time or recorded messages from Earth can fully satisfy. In a very real sense, the greenhouse would likely function as both food source and therapy room at once, one of the only places inside the entire structure where the environment feels less like a machine and more like something quietly alive. Even something as simple as talking to Earth depends on an entire supporting infrastructure most people never think to ask about. A network of large dish antennas spread across different longitudes on Earth, working together so that at least one of them can always maintain a line of sight toward Mars as the planet rotates, along with a small fleet of orbiting relay satellites circling Mars itself, catching signals from the surface and forwarding them onward. Without that relay infrastructure functioning correctly, A habitat could find itself completely cut off from Earth for extended stretches whenever the direct line of sight is blocked. A genuinely frightening scenario for a crew already isolated by tens of millions of kilometers, transforming an already significant communication delay into total silence. Maintaining and eventually expanding that relay network becomes its own quiet, background requirement of any permanent settlement. One more system, invisible until it fails, that has to keep functioning correctly for the psychological and practical connection to Earth to remain intact at all. Return for a moment to the dust, because its health effects extend further than lung damage alone, touching nearly every exposed part of the body over enough time. Fine particles, working their way past a suit's seals, can irritate eyes, leaving them red and inflamed after even brief exposure. Since the same sharp mineral edges that make the dust so abrasive to machinery are equally abrasive to soft tissue. Skin exposed during suit changes or minor equipment failures can develop irritation and rash from prolonged contact with the same reactive salts already known to disrupt thyroid function when inhaled. Sinus passages, constantly filtering whatever fine particles slip past the habitat's air filtration, may become chronically inflamed over years of low-level exposure, a condition already observed in miners and industrial workers dealing with comparable fine particulates back on Earth, except with no option to change occupations or relocate somewhere with cleaner air. None of these individual symptoms sounds dramatic in isolation. A little eye irritation, a little sinus congestion, a rash that clears up in a few days. But strung together across years of chronic, low-level, unavoidable exposure inside a sealed environment, offering no true escape from it, they represent a slow accumulation of health costs that mission planners are only beginning to seriously grapple with, precisely because so much research into Martian dust toxicity has only been conducted in the last several years, using samples and data gathered from rovers that had no way to measure the effects on living tissue directly. It helps to put the radiation numbers discussed earlier alongside something more familiar, because abstract dose figures rarely register on their own. A single chest X-ray on Earth delivers a dose small enough that a hospital barely tracks it. A full-body scan delivers meaningfully more, enough that doctors do monitor cumulative exposure across a patient's lifetime, particularly for anyone requiring frequent imaging. Workers in the nuclear industry on Earth operate under strict annual exposure limits, carefully monitored with dosimeters and regularly reviewed by safety officers, precisely because chronic exposure at elevated levels carries measurable, long-term cancer risk. The dose measured on the open Martian surface, absorbed simply by existing there unshielded, runs at a rate that would blow through many of those same occupational safety limits within a single year. Not through any single dramatic event, but through the ordinary, unavoidable background environment of the planet itself. This is precisely why the underground and heavily shielded architecture described earlier is not an exotic engineering preference, but a basic requirement for any mission lasting longer than a few months, and why every serious mission plan treats radiation exposure as a resource to be rationed as carefully as oxygen or drinking water, tracked and logged for every single person, every single day, for as long as they remain on the surface. It is worth asking honestly what a genuinely good outcome might actually look like, decades into a project like this, because the honest answer is far more modest than most popular imagery suggests. A good outcome is not a green, breathable Mars with open cities beneath a blue-tinted sky, because altering an entire planet's atmosphere and temperature on any meaningful timescale remains firmly in the territory of long-term theoretical proposals, requiring resources and technology far beyond anything currently available, and timelines measured in centuries rather than decades, even under optimistic assumptions. A genuinely good outcome, within the lifetime of anyone reading this, looks instead like a handful of habitats gradually growing more reliable, drawing on lessons learned from the failures and near failures of the ones that came before them, supporting slightly larger crews, for slightly longer stays, with slightly wider margins for error, as engineering knowledge accumulates the way it always has in human exploration, through hard-won experience rather than sudden breakthrough. It looks like better regolith shielding techniques, reducing radiation risk incrementally, better closed-loop recycling, reducing dependence on resupply from Earth, better psychological support structures built directly into mission design rather than added as an afterthought. It looks, in other words, far less like the sudden arrival of a new frontier, and far more like the slow, unglamorous accumulation of hard-won engineering knowledge that eventually, generations from now, might make something resembling a genuine home possible, assuming the underlying biology of partial gravity and chronic radiation exposure ever allows it at all. There is a word buried at the center of this entire story that deserves one final, honest look, because almost everything discussed so far ultimately comes down to what that single word actually means in two very different places. On Earth, living means breathing without ever thinking about it. It means drinking water straight from a tap without a second thought. It means walking outside and feeling warmth on skin without calculating an invisible dose absorbed in the process. It means eating food grown under open sky, hearing rain against a window, standing in wind that carries the smell of somewhere else entirely. It means sharing a planet with billions of other people, any one of whom might become a new friend tomorrow. It means knowing that if illness strikes, a hospital exists somewhere nearby, staffed by specialists who have spent entire careers treating exactly that condition. All of this sits so deeply embedded in ordinary daily experience that it barely registers as support at all. It simply feels like reality, the quiet, invisible backdrop against which an entire life unfolds. On Mars, every part of that backdrop would have to be built by hand and maintained without pause. Air would be manufactured. Water would be recycled from waste. Food would be grown under artificial light inside a room barely larger than a closet. The sky, if visible at all, would appear through a small reinforced port rather than an open window, a pale, rust-tinted haze rather than open blue. Social contact would mean the same small handful of faces for years running, with nowhere else to go and no possibility of simply meeting someone new. Medical care would mean whatever fits inside a single cabinet, staffed by whoever happened to receive the broadest training before departure, rather than a specialist devoted to any single condition. Every element that makes life feel like life on Earth would either be absent entirely or painstakingly simulated by machinery running around the clock. Machinery that ages, that wears, that occasionally fails, exactly when it is needed most. This is not a frontier in the way that word has traditionally been used, because a frontier implies open space, room to roam, the promise of gradual expansion outward into something wider and freer than what came before. Mars offers none of that to anyone actually living there day to day. It offers a sealed shell, a fragile bubble of engineered air and warmth and pressure, carried across the void and set down on ground that has been cold, airless, and silent for longer than life itself has existed anywhere in the solar system. The genuine frontier is not the open landscape outside the viewport. It is the thin, engineered wall separating a living body from a vacuum that has been waiting, patiently, for 4 billion years. It is also worth considering the sheer economics of simply keeping a small settlement supplied, because the cost of moving mass off Earth remains. Even after decades of steady improvement in launch technology, extraordinarily high compared to almost anything else humans routinely transport. Every kilogram sent toward Mars has to first be launched off Earth against its own gravity, a process that consumes enormous amounts of fuel and money before the spacecraft even leaves orbit, then coasted across tens of millions of kilometers of open space for months, then decelerated and landed safely on a world with just enough atmosphere to complicate the landing without offering enough of it to meaningfully help. Launch windows between Earth and Mars only open roughly once every 2 years. When the orbits of the two planets align favorably enough to make the trip efficient, meaning that missing a particular window does not simply delay a shipment by a few weeks, the way a missed delivery might on Earth, but by roughly 2 full years until the next viable opportunity arrives. This orbital rhythm shapes nearly every planning decision a Mars mission makes, because critical spare parts, medical supplies, and scientific equipment all have to be predicted, packed, and launched years in advance of when they might actually be needed, based on engineering estimates about failure rates that can only be refined once real habitats have actually operated on the surface long enough to generate real data. Early missions, in other words, would be making some of their most important supply decisions partly blind, refining their estimates only through direct experience, which means the first several waves of habitats and crews would likely serve as much as a source of hard-won engineering lessons as they would a genuine step toward permanent settlement. Many mission architects have argued that the Moon offers a more sensible proving ground before any of this is attempted on Mars. And the reasoning behind that argument is worth understanding, because it highlights just how much remains untested, even in a location dramatically closer to home. The Moon sits only a few days away rather than the better part of a year, meaning equipment failures can be resupplied on a timescale of weeks rather than years, and any medical emergency serious enough to require Earth-based treatment could realistically be evacuated in time to matter, something categorically impossible once a crew has committed to a Mars mission. Lunar gravity, at roughly 1/6 of Earth's, is even lower than Martian gravity, meaning any habitat and any human body proven capable of functioning there would still leave open questions about how the body responds specifically to Martian conditions, but a permanent lunar base would still generate invaluable data on partial gravity physiology, closed-loop life support reliability, over years rather than months, and the psychological effects of long-term isolation in a hostile environment, all gathered close enough to Earth that a genuine emergency evacuation remains realistically possible. Several space agencies have already begun treating the Moon this way, less as a destination in its own right, and more as a rehearsal space where the hardest lessons about living off Earth can be learned at a survivable distance, before anyone commits irreversibly to a world where rescue is not simply difficult, but genuinely impossible for most of any given year. Return once more to the analog missions already conducted here on Earth, because their findings deserve a closer look than a passing mention allows, given how directly they inform what a real Mars crew would eventually face. Volunteers in these simulated habitats follow schedules deliberately built to mirror an actual mission as closely as possible, including simulated spacewalks conducted in cumbersome mock suits, communication delays artificially inserted into every exchange with the outside world, and strict rationing of consumables meant to mimic the genuine scarcity of a real mission rather than the comfortable abundance of ordinary life on Earth. Across multiple such missions, researchers have consistently observed a dip in morale and cognitive performance occurring somewhere in the later stretch of the mission timeline. well after the initial novelty has worn off, but still well before the relief of a known return date feels close enough to matter emotionally. During this stretch, crews have reported increased friction over small, ordinary disagreements that would barely register outside the habitat. A washing rotation handled slightly unevenly, a differing opinion on how to prioritize two competing repair tasks, disagreements that under normal circumstances would resolve themselves quickly, but inside a sealed, monotonous environment can fester into genuine tension lasting days. Sleep quality tends to decline across these same missions, likely tied to the artificial lighting environment and the complete absence of natural circadian cues, and several participants across different missions have independently described a sense of time distorting, days blending together into a kind of featureless continuity that made keeping track of the calendar surprisingly difficult without deliberate effort. These findings, gathered under conditions that still allow volunteers to walk outside afterward and breathe unfiltered air under an open sky, represent something close to a best-case scenario compared to what an actual multi-year Mars mission would impose, since real settlers would carry the additional, inescapable knowledge that no walk outside ever offers that same simple relief. The suit itself, already described in terms of what it prevents a person from feeling, also deserves a closer look at what maintaining one actually requires. Because a suit, capable of holding pressure against near vacuum for years at a time, does not simply get worn and hung back up afterward. Every seal, every joint, every zipper-style pressure closure has to be inspected after each use for the earliest signs of wear, because a failure discovered on the surface, tens of minutes from the nearest airlock, carries consequences a failure discovered during routine inspection never will. Fabric layers designed to block radiation and insulate against extreme cold slowly degrade with repeated flexing at the joints, the same way any material weakens with repeated stress. And Martian dust working its way into zippers and seals accelerates that wear considerably faster than equivalent equipment would degrade in a clean environment on Earth. Life support backpacks attached to each suit, responsible for regulating oxygen flow, scrubbing exhaled carbon dioxide, and managing internal temperature, require their own maintenance schedule entirely separate from the suit fabric itself, with battery packs that need regular charging and eventual replacement, and filters that need swapping on a fixed schedule regardless of how heavily the suit has actually been used. A single suit, in other words, functions as its own miniature life support system, complete with its own maintenance log, its own spare parts inventory, and its own failure history, and a habitat supporting even a small crew would need multiple suits cycling through use, cleaning, and repair simultaneously. Since a single malfunctioning unit could mean the difference between a crew member being able to assist with an outdoor repair and being confined entirely to the interior until a replacement or repair becomes available. It is worth pausing on the question of what actually counts as an emergency in an environment where nearly everything already sits close to the edge of tolerable risk, because the definition shifts considerably compared to life on Earth. On Earth, a power outage is an inconvenience, solved by candles, a generator, or simply waiting for the grid to come back online, rarely posing any direct threat to survival within the time frame involved. Inside a Mars habitat, a power outage lasting more than a few hours begins directly threatening oxygen generation, heating, and water recycling all at once, meaning something Earth dwellers file under minor annoyance becomes, on Mars, an immediate all-hands emergency requiring the full attention of the crew. A minor injury on Earth, a sprained ankle, a small cut requiring stitches, rarely disrupts daily life beyond a visit to a clinic and a few days of reduced activity. On Mars, The same injury could remove a crew member from active duty at precisely the moment their specific expertise is needed for an unrelated repair, and because crews are kept deliberately small to minimize resupply mass, losing even one person's full functionality for a stretch of days can cascade into delays across several other systems simultaneously, each one waiting on expertise or physical labor that the injured crew member would normally have provided. This recalibration of what counts as serious extends to nearly every category of risk discussed throughout this story, meaning a Mars crew has to operate with a baseline vigilance that would be considered exhausting, even paranoid, by ordinary Earth standards, simply because the actual margin between routine and catastrophic is so much thinner than anywhere most people have ever lived. There is also the question of what happens to relationships that predate the mission entirely, the parents, siblings, and old friends left behind on Earth, whose lives continue moving forward at a normal pace while the person on Mars experiences time within an entirely different rhythm of confinement and delay. A parent back on Earth ages normally, faces ordinary health concerns, celebrates ordinary milestones, all while the settler on Mars receives updates about these events only after a significant delay, unable to offer real-time comfort during a difficult moment, unable to simply show up for an emergency the way a family member on Earth could. Should a parent become seriously ill, or should any loved one face a genuine crisis, the settler would face the added weight of knowing that even in the best-case scenario, any return journey would take the better part of a year, arriving, if it arrived in time at all, only after the crisis had likely already resolved itself, one way or another. This particular form of distance, less discussed than the physical dangers but no less real, represents its own quiet, ongoing grief, a slow accumulation of moments missed, milestones observed only second-hand and after the fact, and a relationship with home that gradually transforms from lived experience into something closer to correspondence with a place increasingly difficult to picture as still real and present, rather than as a memory slowly receding into the past. Mission psychologists studying long-duration isolation increasingly recommend preparing crews explicitly for this particular form of loss before departure, treating it as seriously as any physical training, because the emotional toll of watching a life continue without you, from a distance too great to meaningfully participate in it, has repeatedly proven to be one of the harder adjustments even experienced isolation veterans describe. The exercise regimen mentioned earlier deserves a closer look on its own, because it represents one of the clearest examples of how something ordinary on Earth transforms into a serious medical countermeasure on Mars. On Earth, exercise is largely a matter of personal choice, something people do for fitness, enjoyment, or long-term health, with real but gradual consequences for skipping it. On Mars, skipping a scheduled exercise session carries measurable, accelerating physiological cost, because the partial gravity environment is already working against bone density and muscle mass every single hour of every single day, meaning resistance training and cardiovascular conditioning function less like a lifestyle choice and more like a mandatory medication, tracked, logged, and reviewed the same way a dosage schedule would be. Equipment capable of providing meaningful resistance without relying on Earth, normal gravity has to be specially engineered, since a simple barbell that weighs very little under Martian gravity provides far less genuine resistance than the same equipment would on Earth, requiring specialized machines using pneumatic resistance, elastic tension, or flywheel-based systems instead, all of which add mass, complexity, and additional maintenance requirements to a habitat already stretched thin, managing everything else. Missing scheduled sessions, whether due to illness, competing emergencies, or simple exhaustion after an especially difficult day, does not simply delay progress the way missing a workout might on Earth, but actively accelerates bone and muscle loss that may prove difficult or impossible to fully reverse, even after returning to full Earth gravity years later. Adding yet another item to the long list of daily obligations that cannot realistically be postponed without lasting physical consequence. Consider, too, how differently illness spreads and gets managed inside a sealed environment where nobody can simply step outside for fresh air or separate themselves meaningfully from the rest of the group. On Earth, a contagious respiratory infection moving through a household can be managed by opening windows, spending time outdoors away from others, or, in serious cases, seeking care at a hospital equipped for exactly that situation. Inside a sealed Martian habitat, the same recycled air moves continuously through every occupied room, meaning any airborne illness introduced by one crew member has a real chance of eventually reaching everyone else, with no separate building to retreat to and no truly fresh air anywhere to help clear it faster. Quarantine procedures would need to be built directly into the habitat's design from the outset, ideally with a separate sealed compartment capable of isolating a sick crew member from the shared air supply, along with independent filtration for that space specifically, adding yet another system that has to be designed, built, tested, and maintained before it is ever actually needed. Given how small most crews would realistically be, losing even a single healthy member to illness for an extended stretch represents a genuine operational strain. One more example of how problems that would barely register as inconvenient on Earth become serious logistical challenges once transplanted into a sealed habitat on a planet offering no outside support of any kind. The gap between how Mars settlement gets portrayed publicly and how it actually functions in mission planning documents is itself worth examining, because that gap shapes public expectations in ways that could eventually matter for the people who actually go. Promotional materials produced by space agencies and private companies alike tend to emphasize wide, open vistas, dramatic sunsets, and a sense of pioneering freedom reminiscent of earlier human frontiers, imagery that generates public enthusiasm and, in the case of private missions, investor confidence. But that bears only a loose resemblance to the sealed, heavily monitored, resource-constrained reality described throughout engineering studies and mission architecture documents. This is not necessarily dishonest in any deliberate sense, since early concept art naturally emphasizes the inspiring long-term vision rather than the grinding daily reality of the earliest missions. But it does create a real risk of mismatched expectations for anyone drawn toward the idea of Mars settlement, primarily through that inspiring imagery rather than through the underlying technical literature. The people ultimately selected for these missions would need genuine, unfiltered access to the full picture described throughout this story, not simply as a formality buried in dense technical briefings, but as a core part of understanding exactly what they are choosing. Because informed consent in an environment this unforgiving depends entirely on the accuracy of the picture given beforehand, and no amount of enthusiasm generated by inspiring artwork changes the physics waiting on the other side of the landing sequence. There is a deeper question sitting underneath the entire discussion of resupply and logistics, and it concerns exactly how self-sufficient an early Mars settlement could realistically become, and how long that process might genuinely take. True independence from Earth would require not just growing food and recycling water and air, all of which remain achievable with current or near-term technology, but manufacturing an enormous range of manufactured goods locally: electronics, precision machined components, specialized chemicals, medical supplies, none of which can currently be produced from raw Martian materials without an industrial base far more sophisticated than anything a small early settlement could plausibly support. Even optimistic projections, studied by mission planners, generally suggest that meaningful local manufacturing capability, beyond simple structural materials and basic life support consumables, would take many decades to develop, requiring a settlement large enough to support specialized manufacturing roles, a stable and abundant power supply well beyond what early habitats could generate, and a reliable local supply chain of raw materials that itself requires extensive mining and processing infrastructure to establish. Until that industrial base exists, and for the foreseeable future that likely means for the entire working lifetime of anyone reading this, a Mars settlement remains fundamentally dependent on shipments from Earth for anything beyond the most basic consumables, meaning true self-sufficiency, in the sense most people imagine when picturing an independent Martian colony, remains a genuinely distant goal, rather than something achievable within the time frame of the earliest permanent habitats. Sleep itself, something almost nobody thinks of as a scarce resource on Earth, becomes a carefully tracked variable inside a Mars habitat, monitored closely because so many of the environment's other stresses converge directly on how well a person actually rests. The absence of genuine natural light disrupts the body's internal clock in ways artificial lighting can only partially correct, even with careful engineering meant to simulate a full daylight cycle. The constant low hum of fans, pumps, and compressors running throughout the structure, essential for keeping everyone alive, also means true silence never really exists. And the human brain, even during sleep, remains subtly aware of every shift in that background noise, alert on some level to any change that might signal a developing problem. Shared, tightly confined sleeping quarters offer far less acoustic and physical separation than most people are used to on Earth, meaning one crew member's restless night can easily disturb another's, compounding fatigue across the entire group rather than remaining an isolated individual issue. Sleep researchers studying isolated environments consistently find that fragmented, lower-quality sleep worsens nearly every other challenge already discussed throughout this story. Slowing reaction times during maintenance tasks where precision genuinely matters, shortening emotional patience during a day already filled with competing demands, and gradually eroding the very cognitive sharpness a crew depends on to correctly diagnose a failing system before it becomes a genuine emergency. Meaning something as basic as a good night's sleep becomes, quietly, one of the most consequential variables in the entire mission. Consider also how differently risk itself would need to be evaluated and communicated inside a crew this small and this isolated. Because ordinary human decision-making, tested and refined over an entire lifetime spent on Earth, does not automatically translate well into an environment where the ordinary safety margins simply do not exist. On Earth, a person can afford to take a calculated risk, a solo hike slightly further than planned, a repair attempted without waiting for a second pair of hands, because even if the gamble fails, help usually remains within reach, whether through a phone call, a nearby road, or simply the presence of other people close enough to notice something has gone wrong. On Mars, the same instinct toward reasonable, everyday risk-taking has to be deliberately retrained, because the margin for error shrinks dramatically the moment a person steps outside a fully monitored, fully redundant part of the habitat. And a decision that would carry only minor consequences on Earth can carry consequences that cannot be undone on Mars. simply because the backup systems that quietly absorb small mistakes everywhere else in a person's life do not exist there in anything like the same abundance. Mission planners have increasingly focused on building this recalibrated sense of risk directly into training, running crews through scenario after scenario specifically designed to surface the small, habitual shortcuts a person might take without thinking twice on Earth, and to replace them with a far more deliberate, checklist-driven approach to nearly every physical task, because on Mars, the habits that keep a person alive have to be different from the habits that serve them perfectly well their entire life up to that point. There is one more piece of the compounding puzzle worth walking through directly, because it shows exactly how the different hazards described throughout this story tend to arrive together rather than politely, one at a time. Picture a routine outdoor task, replacing a worn seal on an external equipment housing, scheduled for a morning when everything else appears stable. Partway through the repair, a moderate dust gust reduces visibility and begins coating the open housing with fine, electrostatically charged particles, threatening to contaminate the very seal being replaced. The crew member has to work faster than planned, extending their time outside closer to the safe limit of their suit's air supply, while simultaneously accumulating slightly more of their weekly radiation budget than intended for a task that was supposed to be quick and routine. Back inside, the dust that inevitably rode in on the returning suit adds to the slow, ongoing accumulation already building up in the habitat's air filtration system, nudging the next scheduled filter replacement slightly earlier than planned. None of these individual shifts amounts to a crisis on their own, but stacked together, a slightly longer radiation exposure, a slightly earlier filter replacement, a slightly more contaminated seal that may need reinspection sooner than expected. They represent exactly the kind of quiet, compounding cost that defines an ordinary week on Mars. Each small adjustment reasonable in isolation, and collectively responsible for the sense, described by nearly every serious study of long-duration isolation, that life in this kind of environment slowly grinds down the margin for error a little further with each passing month. Rather than presenting itself as a single dramatic turning point anyone could point to and call the moment things became difficult. Funding realities shape almost every decision described throughout this story. Whether that funding comes from a government space agency answering to elected officials and public budgets, or from a private company answering to investors expecting eventual returns, because every additional layer of safety, every extra redundant system, every additional kilogram of shielding costs real money that has to be justified against a finite budget. This creates a persistent, uncomfortable tension between the level of safety engineers would prefer to build in and the level that any given mission can actually afford, a tension that has shaped every human spaceflight program in history, and one that becomes considerably sharper once the stakes involve permanent settlement rather than a short-duration mission with a clearly defined return date. Historically, major advances in the safety and reliability of human spaceflight have often followed serious failures rather than preceding them. Painful lessons absorbed only after something has already gone wrong, and mission planners openly acknowledge that early Mars missions will very likely follow a similar pattern, refining their safety margins gradually through hard experience rather than through purely theoretical foresight, meaning the earliest settlers would, in a very real sense, be helping establish the safety standards that later missions will eventually benefit from. Somewhere further down this timeline, assuming enough of these engineering and biological questions eventually find workable answers, a strange new category of person would begin to emerge, someone who has never once stood on Earth, never felt full Earth gravity, never breathed unfiltered outdoor air, and never seen an open sky that was not at best, a distant memory passed down through the stories of parents who once knew that world firsthand. Their sense of home would be shaped entirely by sealed corridors, artificial lighting, and the particular rhythm of a habitat's mechanical systems. The same way a person raised near the ocean develops an instinctive relationship with tides and salt air that someone raised inland never quite acquires. Whether such a person could easily identify with Earth at all, culturally or emotionally, remains an open question, and some researchers studying the psychology of extreme isolation suspect that a genuinely native-born Martian population, once it exists in meaningful numbers, would develop its own distinct culture and identity relatively quickly, shaped by shared hardship and shared dependence on the same fragile machinery, rather than by any inherited connection to a planet none of them had ever actually experienced firsthand. That possibility, a genuinely new branch of human culture and identity forming inside a sealed habitat on another world, sits at the far edge of everything discussed throughout this story, distant enough from present-day mission planning to remain mostly speculative, but close enough to the underlying biology and psychology already documented today that it deserves at least this much honest consideration before the conversation moves on. It is worth stepping back one final time before returning to the emotional core of this story, because a fair accounting of Mars' settlement has to hold two things true at once without letting either one cancel the other out. Every hazard described throughout this story is real, well documented in existing research, and taken seriously by the actual engineers and scientists working on these problems today, not exaggerated for dramatic effect. And at the same time, none of these hazards are treated by the people actually planning these missions as reasons to abandon the idea entirely, but rather as an extraordinarily long list of problems that have to be solved one at a time through careful engineering, honest risk assessment, and a willingness to learn from mistakes that will inevitably happen along the way. This is, in a sense, precisely how every previous frontier in human history has actually been crossed, not through some sudden absence of danger, but through a slow, difficult, often costly process of learning to survive conditions the human body was never originally built for. Whether that meant learning to survive open ocean voyages, extreme cold, high altitude, or the vacuum of space itself during the earliest years of orbital spaceflight. The difference with Mars is simply one of degree, a longer list of simultaneous hazards, a longer distance from help, and a narrower margin for error than any previous frontier has demanded. Which is exactly why the honest version of this story matters more than the inspiring postcard version, because the people who eventually choose to go deserve to make that choice with a full and accurate picture of exactly what they are walking into, rather than a comfortable illusion that dissolves the moment the airlock cycles shut behind them for the first time. None of this makes Mars cruel, because cruelty requires some form of intent, some awareness of the harm being caused, and Mars possesses neither. It is simply indifferent, in the most complete sense that word allows. It is a world of cold stone and thin carbon dioxide, and near total silence, and it has existed exactly this way for longer than anything alive has existed anywhere nearby. It does not resist a human presence out of hostility. It resists because it was never shaped by the particular set of conditions that make a world hospitable to something as fragile and specific as human biology. No protective magnetic field, no thick warming atmosphere, no liquid water resting openly on the surface, no oxygen woven through the air, nothing. Just a planet-sized record of what a world looks like when the ingredients for life either never fully came together or came together once, briefly, and then slowly drained away into space over the course of billions of years. To actually live there would mean carrying a small fragment of Earth across the void and setting it down on ground that owes nothing to anyone standing inside it, then spending every remaining day defending that fragment against everything the planet can throw at it, patiently, relentlessly, without pause. It would mean falling asleep each night inside a structure slowly aging around its occupants, its seals wearing microscopically thinner, its filters inching closer to saturation, its solar panels gathering one more thin layer of dust, while outside those walls the planet remains exactly as it was the day before, and will remain exactly the same long after every habitat and every human voice inside it has gone quiet. And somewhere beneath the daily rhythm of readings and repairs and rationed hours outdoors, every person who chooses this path would likely carry a quiet, private awareness of exactly what they traded away to get there, a world that gave them everything without asking anything in return: air and water and warmth and open sky and the sound of wind moving through something alive, exchanged for a world that gives nothing at all and never will, no matter how many generations eventually call it home. And yet people will very likely still go, fully informed, eyes open, choosing it anyway, because the same restless impulse that once pushed small groups of humans across unmapped oceans and over unclimbed mountains has never really gone away. It has simply been waiting for the next horizon worth walking toward. Mars is that horizon now, waiting exactly as it has always waited, patient, unchanged, and utterly indifferent to whether anyone ever arrives at all. If you made it this far into the story, thank you for spending this time here. And if any part of it left you thinking differently about what a life beyond Earth would actually require, consider leaving a like and subscribing for more journeys like this one into the quiet corners of the cosmos. For now, let the weight of this one settle slowly, the way distant starlight settles onto open ground on a clear, dark night, and allow yourself to rest here, safely, beneath a sky that has always given you everything you needed to simply breathe.